Welcome to VLSI DFT lecture series. In this session, I am going to explain about VLSI Design Flow and ASIC Flow. ASIC means Application Specific Integrated Circuits. It is also an integrated circuit that is customized for a particular use rather than intended for general purpose use. Next, VLSI Design Flow and ASIC Flow. So, ASIC is designed for or customized for a particular usage. The ASIC Design Flow is an IC design process which includes various steps like design conceptualization, chip optimization, logic and physical implementation, design validation and verification. So, let's have an overview of each of the steps involved in the process. The first step is chip specification. This is the stage at which engineer defines features, microarchitectures, functionalities means hardware, software interfaces, specifications with design guidelines of ASICs such as speed, then area, then cost, power, technology. Technology means 28 nanometer technology, 22 nanometer, 16, 14, 10. Research are going on up to 3 nanometer and 2 nanometer. The next step is architecture. Now, the architect gives a system level view of how the chip should operate. They will decide that all other components are required, what clock frequency they should run, how to target power and performance requirements. They also decide how the data should flow inside the chip. The next step in the design process is design and functional verification. Functional verification confirms the functionality and the logical behavior of the circuit by simulation on the design entry level. This is a stage where the design team and verification team come into cycle, where they generate RTL code, means resistor transistor level code, using test benches. This is known as behavioral simulation. So it gives the guidelines to locate the logics based on the requirement. The next step in the design is RTL, block synthesis or RTL function. Once the RTL code and the test bench are generated, the RTL team works on the RTL description. They translate the RTL code into gate level netlist using a logical synthesis tool. That logical synthesis tool should meet the required timing constraints. Thereafter, a synthesized database of ASIC design is created in the system. So, when timing constraints are met with the logic synthesis, the design proceeds to next step called design for testability, DFT techniques. So, logic synthesis is the process of translating and mapping the RTL code written in HDL or in HDL means Verilog or in VHDL into technology gate level representation. So, the next step in the design is RTL verification. This step ensures that the design is logically correct without any major timing errors. It also eliminates all syntax errors from your VHDL code. System Verilog and UVM test bench analyzing the code by giving binary values. The next step in the design is called DFT, Design for Testability. It is meant for providing a method for testing each and every node in the design for structural and other faults. So, the higher the number of nodes which can be tested through the targeted number of patterns, then greater the coverage of the design. For this to possible, every node in the design has to be controllable and observable. We consider these as two basic principles of DFT which are to be followed in order to have maximum test coverage. DFT consists of several steps. The first step is scan path insertion. It is a methodology of linking all register elements into one long shift register called scan path. This can help to check small parts of the design instead of the whole design in one go. The second step is memory BIST, means MBIST, built-in self-test. In the lower technology node, chip memory requires lower area and fast access time. MBIST is a device which is used to check RAMs, random access memories. It is a comprehensive solution to memory testing, errors and self-repair proficiencies. The next step in DFT is ATPG, called Automatic Test Pattern Generation. It is a method of creating test vectors or sequential input patterns to check the design for fault generated within various elements of the circuit. Then the seventh step in our design is floor planning, also called blueprint of your chip. So after DFT, the physical implementation process is to be followed. In physical design, the first step is floor planning. It is the process of placing blocks in the chip. It includes a block placement, design portioning, pin placement, power optimization. So floor planning determines the size of the chip, places the gates, connects them with wires. So while connecting, engineers take care of wire length and functionality which will ensure signals will not interfere with nearby elements. In the end, simulate the final floor plan with post-layout verification process. The next step in the design process is placement. Placement is the process of placing standard cells in a row. A poor placement requires larger area and it also degrades the performance. So various factors should consider during placement, like timing requirement, the net length and hence the connections of cells. Power dissipation should be taken care. It removes the timing violations. The next step is routing. Routing is the process of creating physical connections based on the logical connectivity. Signal pins are connected by routing metal interconnects. Routed metal path must meet timing, close queue and also physical DRC requirements. The 10th step in our design is final verification or physical verification and timing. So after routing, ASIC design layout undergoes 3 steps of physical verification known as sign-off checks. This stage helps to check whether the layout works the way it was designed to. They will check layout versus schematic LVS, then design rule checks DRC, then logical equivalence check. The LVS means the process of checking that the geometry or layout matches the schematic or netlist. The second step, DRC, it is the process of checking that the geometry in the GDS file follows the rules given by the foundry. The third step, LVC, is the process of equivalence check between pre and post design layout. The last step in our design is GDSII and post silicon validation. So in the last stage of the tape out, the engineer performs wafer processing, packaging, testing, verification, delivery to the physical IC. So GDSII is the file produced and used by the semiconductor foundries to fabricate silicon and handle to the client. In the case of post-silicon validation, this sample now goes through post-silicon process, where another team of engineers runs different tester patterns. It is more difficult to debug in post-silicon validation than pre-silicon validation. It is because the level of visibility into chips' internal nodes is drastically reduced in the case of post-silicon validation. A million clock cycles would have finished in a second, and tracing back to the exact time of errors will be time-consuming process in this post-silicon validation. So I guess we have gone through the basics of VLSI technology and ASIC flow. Look forward for more details of DFT in ASIC design flow in the next classes. Thank you.